Hello students, in the previous session we studied about event, occurrence of event and types of events. In this session we shall continue with the event A or B. Recall that union of two sets A and B denoted by A union B contains all those elements which are either in A or in B or in both. When the sets A and B are two events associated with a sample space, then A union B is the event either in A or B or both. The event A union B is also called A or B. It is clear from the picture here, the event A or B, the shaded portion is A union B. Therefore, event A or B is equal to A union B is equal to omega such that omega belongs to A or omega belongs to B. Now, the event A and B. We know that intersection of two sets A intersection B is the set of those elements which are common to both A and B, that is, which belong to both A and B. Here we can see the event A and B. The shaded portion is representing A intersection B. If A and B are two events, then set A intersection B denotes the event A and B. Thus, A intersection B is equal to omega such that omega belongs to A and omega belongs to B. For example, in the experiment of throwing a die twice, let A be the event, score on the first throw is 6 and B is the event, sum of two scores is at least 11. Then A is equal to 6, 1, 6, 2, 6, 3, 6, 4, 6, 5 and 6, 6 and B be equal to 5, 6, 6, 5 and 6, 6. So, A intersection B will be equal to 6, 5 and 6, 6. Note that the set A intersection B is equal to 6, 5 and 6, 6 may represent the event the score on the first throw is 6 and the sum of the scores is at least 11. Now, let us study about the event A but not B. We know that A minus B is the set of all those elements which are in A but not in B. Here the picture shows us the event A but not B. You can see the shaded portion is A minus B, which is equal to A intersection B complement. Therefore, the set A minus B may denote the event A but not B. We know that A minus B is equal to A intersection B complement. Now, consider another example here. Consider the experiment of rolling a die. Let A be the event getting a prime number, B be the event getting an odd number. Write the sets representing the events, first A or B, second A and B, third A but not B, fourth not A. Now, look at the solution. Here sample space S is 1, 2, 3, 4, 5, 6 and A is equal to 2, 3, 5 and B is equal to 1, 3, 5. Obviously, first A or B is equal to A union B, that is equal to 1, 2, 3, 5. Second, A and B is equal to A intersection B, that is equal to 3, 5. Third, A but not B is equal to A minus B, that is equal to 2. Fourth, not A means A complement, that is equal to 1, 4, 6. Now, let us discuss about mutually exclusive events. In the experiment of rolling a die, a sample space is S is equal to 1, 2, 3, 4, 5, 6. Consider event A, an odd number appears, and B, an even number appears. Clearly, the event A excludes the event B and vice versa. In other words, there is no outcome which ensures the occurrence of events A and B simultaneously. Here, A is equal to 1, 3, 5 and B is equal to 2, 4, 6. Clearly, A intersection B is equal to 5. That is, A and B are disjoint sets. In general, two events A and B are called mutually exclusive events if the occurrence of any one of them excludes the occurrence of the other event. That is, if they cannot occur simultaneously. In this case, the set A and B are disjoint. Again, in the experiment of rolling a die, consider the events A, an odd number appears, and event B, a number less than 4 appears. Obviously, A is equal to 1, 3, 5 and B is equal to 1, 2, 3. Now, 3 belongs to A as well as 3 belongs to B. Therefore, A and B are not mutually exclusive events. There is a remark here for you. Simple events of a sample space are always mutually exclusive events. Here you can see in the picture, mutually exclusive events are shown by A and B. Here A intersection B is equal to 5. They are disjoint. Now let us discuss about exhaustive events. Consider the experiment of throwing a die. We have S is equal to 1, 2, 3, 4, 5, 6. Let us define the following events. Event A, a number less than 4 appears. Event B, a number greater than 2 but less than 5 appears. And C, a number greater than 4 appears. Then A is equal to 1, 2, 3, B is equal to 3, 4 and C is equal to 5, 6. We observe that A union B union C is equal to 1, 2, 3 union 3 union 4 union 5, 6, that is equal to S. Such events A, B and C are called exhaustive events. In general, if E1, E2 and so on En are n events of the sample space S, and if E1 union E2 union E3 union so on union En is equal to union I from 1 to n Ei is equal to S, then E1, E2 so on En are called exhaustive events. In other words, events E1, E2 so on En are said to be exhaustive if at least one of them necessarily occurs whenever the experiment is performed. Further, if Ei intersection Ej is equal to phi for I not equal to j, that is, events Ei and Ej are pairwise disjoint, and union I ranging from 1 to n Ei is equal to S, then events E1, E2, so on, En are called mutually exclusive and exhaustive events. Let us consider some examples here. Two dice are thrown and the sum of the number which come up on the dice is noted. Let us consider the following events associated with this experiment. A. The sum is even. B. The sum is multiple of 3. C. The sum is less than 4. D. The sum is greater than 11. Which pairs of these events are mutually exclusive? Let us see here, there are 36 elements in the sample space. S is equal to x comma y, where x and y are equal to 1, 2, 3, 4, 5, 6. Then A is equal to 1, 1, 1, 3, 1, 5, 2, 2, 2, 6, 2, 4, 3, 1, 3, 3, 3, 5, 4, 2, 4, 4, 4, 6, 5, 1, 5, 3, 5, 5, 6, 2, 6, 4, 6, 6. And B is equal to 1, 2, 2, 1, 1, 5, 5, 1, 3, 3, 2, 4, 4, 2, 3, 6, 6, 3, 4, 5, 5, 4 and 6, 6. And C is equal to 1, 1, 2, 1, 1, 2 and D is equal to 6, 6. We know that A intersection B is equal to 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 6, 6, that is not equal to 5. Therefore, A and B are not mutually exclusive events. Similarly, A intersection C is not equal to 5. A intersection D is not equal to 5. B intersection C is not equal to 5 and B intersection D is also not equal to 5. Thus, the pairs AC, AD, BC, BD are not mutually exclusive events. Also, C intersection D is equal to 5 and so C and D are mutually exclusive events. Let us take up one more example. A coin is tossed 3 times. Consider the following events. A. No head appears. B. Exactly one head appears. And C. At least 2 heads appear. Do they form a set of mutually exclusive and exhaustive events? The sample space of the experiment is S is equal to H H H, H H T, H T H, T H H, H T T, T H T, T T H and T T T, and A is equal to T T T, B is equal to H T T, T H T, T T H, and C is equal to H H T, H T H, T H H, H H H. Now, A union B union C is equal to T T T, H T T, T H T, T T H, H H T, H T H, T H H, H H H, that is equal to S. Therefore, A, B and C are exhaustive events. Also, A intersection B is phi, A intersection C is phi and B intersection C is phi. Therefore, the events are pairwise disjoint, that is, they are mutually exclusive. Hence, A, B and C form a set of mutually exclusive and exhaustive events. Now, students, it is time to note down the home assignment. Take down the question. 3 coins are tossed once. Let A denote the event 3 heads show. B denote the event two heads and one tail show. C denote the event three tails show, and D denote the event a head show on the first coin. Which events are mutually exclusive? Second, simple, and third, compound. Hope you enjoyed this session. We shall continue axiomatic approach of probability in the next session. Thank you.